but this is the doc.
It's just a derived one.
I think it's sorry.
All right, let's see. Let's see if I can get this to be better today. Will we decide something like this? That doesn't work.
Move the table back a little bit.
Yeah.
Better feel.
Maybe. That's not bad. That's not bad. Easier than moving the whole screen.
Can I ask you a homework question before we start?
You can try. Is this on the null vector one?
It's deriving relativistic
Which one is it?
2.5.
From chapter 2?
Correct.
Oh, okay. I've got some stuff here. So it's 2.5. Where's my solutions to that one? The derivation of the invariant interval delta S squared, is that the one?
No, it says deriving 223 E.
Oh, it's something like contrarian components.
Yes. Okay.
I'm completely confused. Which one are you talking about? Like, what chapter is it from? Chapter 2? Chapter 2.
There's like 4 equations where it's showing like, oh, here's the contrarian component.
Derived the manipulation rules. Those guys. Oh, okay. I got confused with the equation number versus. Let's see. Do I have a solution to that? I thought I had that one. Rotation, cross product of curl. Integral over sphere. Another derivation of the invariant integral. I skipped that one. Oops.
It just seems like it's going from slot A into index notation.
Mm-hmm.
I'm not quite sure what it is.
All right. Let me take a look. Steve, did you do this one?
Yeah, it's kind of handy because like for the first one, you would define the covariant components by taking the contravariant times, so applying the basis vectors and everything. So I'm like, well, you could just not do that, or you do this and then just apply the metric again, and hey, look, covariant components.
You want to do you have your solutions with you? Because I actually don't have a solution to this one yet.
Those on GitHub, yes.
Did it on GitHub?
That was definition. Well, yeah, well, that's the thing. Like, it's I'm not signing.
I like there's a lot of like relativities, like what it.
Yeah.
But what does it mean?
Well, from the definition.
Sorry, I'm getting to it.
Okay, so this is
By inspection. All right.
I do say that to people. It's like, oh, by looking at it, it's clear.
I mean, that's okay. Derive the relativistic component. Like, I don't think it's supposed to be any like more in depth than that. I think this is why I didn't even bother.
So what I did on that was saying if you stick the basis vectors in, it gives you the covariant components.
Yeah.
And then if you apply the metric at each of the basis vectors, or you stick one basis vector into the metric, and then you stick those vectors into the tensor and like the full geometric version, then that pops out the contravariant one.
Mm-hmm.
It seems a long, convoluted way to say that, well, don't stick in the basis vectors.
Right. I mean, I think all of that follows probably more easily from the stuff that we've now done in chapter 24, where we started being more careful with contravariant and covariant stuff. I can take a look at it and write down my detailed derivation and share it, but I didn't bother.
I think all of these are pretty much take whatever the definition is,
Yeah.
apply some number of the metrics to it.
Mhm.
Okay, and that worked.
Mhm.
At least that's what I.
Yeah. That's what you should do. Yeah. Yeah, let me try to write down a detailed solution, see if there's any gotchas. But I don't think so. I mean, I thought it was exactly what Steve's saying. I didn't do it. Okay. Any other questions that I can't answer? We're missing a couple people, but we'll just go ahead and get started. The notes are posted online for today. Let's see, that's probably good there. Okay. So I already got them posted up there. I got the lecture posted for 4 and 5.
You have to have the notes for that because it's kind of hard to read the board.
Yes. Yeah. Yes.
Are you over compressing it, or is that just your
It's a crappy
definition? Okay.
It's a crappy.
It was also the angle, like, same
Right.
thing on the left.
This side was a lot easier
Yeah.
to do than that side.
That's why I tried to.
Yeah.
get
That's
center today.
Steve's
But
suggestion. Let's see if
it's
it looks.
fine if you have the notes on the side.
How's the audio?
I is great.
Okay.
I mean, it's not the best,
Right. But you can
it's-
hear it clearly.
everything.
Okay. Yeah. That's kind of my intention, is that you've got to have the notes to watch the lectures, because I don't have a good camera on the screen. I was hoping this classroom actually had like one of those cameras that follows around, like, a Cylon. But it doesn't. So here we are. It looks like I was the last one to even use this board. I still see stuff from Tuesday on here. Certainly hasn't been cleaned since then. All right, let's go ahead and get started. Hi, Alex. Not you, there's an Alex.
Hi.
Hey,
Hi, Alex.
you can even speak. It's like coming through the whole classroom speakers. Cool. Okay, so we're going to do the rest of chapter 24 today, I hope, hitting the highlights. And then next week, we're going to go into general relativity, like the fundamentals of GR. And so for next week, we're going to do chapter 25 out of Blandford and Thorne, or Thorne and Blandford, depending on your version. And then that'll be it for that, and we'll transition then to Baumgart and Shapiro. I think that'll be sufficient background in GR and all of this notational stuff for us to dive into that. The first chapter in Baumgart and Shapiro we're going to do is kind of a review of GR, but it's way too terse unless you've had a class, I think, in all of this stuff. So we're going to mainly use that chapter to start talking about some astrophysics involving GR, namely the Tolman-Oppenheimer-Volkov equations, which are going to be something that you're going to do for your mid-semester project of implementing a solver for that, which is just like hydrostatic equilibrium. Okay, so let's finish up chapter 24. Couple things that we're going to have to talk about for today. Remember, where we left off is that we were developing the ability to do differentiation and also eventually integration in completely general non-orthonormal bases. And that gets complicated fast. Euclidean life is much, much easier. And so we have to develop some tensor algebra machinery that we didn't need to worry about before. And you don't need to worry about in a lot of physics, except for things like elasticity in complex. Come on in. We can do this. Okay, so a commutator. Now this is probably something, if you've taken quantum mechanics, you're familiar with the idea of a commutator. Notation will be slightly different, but it's the same operator. Okay, so we're going to write it like this. So the commutator of two vectors, A, B, square bracket. It's a vector operator, right? And its components, if I were to write this out, are A alpha partial with respect to alpha, comma, B beta partial with respect to the coordinates in beta, right? That's just writing out the definition of those vectors, right? That's I can write any vector in terms of its components that way. And then the commutator operator does the following to those vectors. A alpha partial of B beta with respect to the alpha coordinates, oops, minus B alpha partial of A beta with respect to the X alpha coordinates, not a square bracket, just parentheses. And then here goes my basis vector in the beta direction, all right? Assumes that this operates on some sort of a scalar field, right? And what this commutator does is measure the following. I think pictures are always instructive. So if I've got some general two vectors, maybe they've got a common origin like this, right? What I am looking for here is to say, if I were to transport vector A along vector B, and I'm going to get myself in trouble here, I can see it already, but that's okay, we can work with it. How much would the components of vector A change? Okay, so if I were to take this vector A, and if it were completely parallel, it would go like this, but it doesn't have to transport that way. If I transport it along B, and instead I get a vector like this, which is curved a little bit, not perfectly parallel. Of course, I bunched myself up here. Hey, Albert, come on in, don't worry about it. And get some new vector like that. That's going to cause me problems later. Tell you what, why don't I just fix my mistake? Make this vector shorter. Okay, so transport A along here, get some new A that's been transported along B. Do the same thing with B, but now it transports not quite parallel. That's like really not parallel. Something like that. And then what the commutator is, it's this vector separation now between these two new vectors. Okay? This is the commutator. And so if the transport really were parallel, these two new vectors would end up arrow to arrow, tip to tip, right? And so the commutator would be 0 in that case, okay? And so we say that if the commutator of A and B is 0, then you can use them as coordinate bases, or the basis that you are testing or computing the commutator of can be a quote-unquote coordinate basis. Okay, so for instance, I could stick basis vectors in here and compute my commutator, and get my E vectors. And if the commutator of two basis vectors is 0, then they're coordinate basis vectors. Life is always easier if you're working with coordinate basis vectors, but they do not have to be necessarily. In complete generality, you have this idea of the commutator. But this is the definition of what a coordinate basis is. When you stick in the basis vectors, their commutator is 0. And that means, what does that mean for coordinate system? It means that I can use the components of those of that basis vector as my coordinates, right? If I change one, I can keep another fixed. You know what I'm saying? Like, I can change one component and move it along of some vector, and the other components of that vector will stay fixed in a coordinate basis. But that's not what happened here with our vectors, right? As I tried to change only one component of the vector, other components changed. And so that means it's non-coordinate. That's all. Yeah, again. Other thing we're going to need, connection coefs. Okay. So this is how we're going to treat non-Cartesian coordinates. And even if you haven't used these per se, you've used them without realizing them. And we're going to utilize the completely general idea of connection coefficients to deal with curved manifolds and curved spacetimes. All right, so let's use an example to introduce the idea of connection coefficients. So consider cylindrical coordinates where I'm going to use omega, phi, and z, which we used last time for our cylindrical coordinate system. And here, of course, we know, I'm going to save myself from drawing the picture unless you guys really need it. X squared plus y squared is the coordinate omega, the cylindrical radius, right, in some 3D space. And then phi just measures distance from the x-axis, angular distance. And so that's going to be the arctangent of y over x. I can draw a quick picture. Why not? You all are familiar with this, though. So this is x, y, z. And I've got some vector in this space. And that's a right angle. This is the angle phi. And this guy, distance from the coordinate origin to here, is the component omega. And then this, up this way, is the z component, which is the same as the Cartesian z, straight up the z-axis. Okay, so here, my basis vectors in cylindrical coordinates then, if I were to write those down, e omega is x over omega in the x direction plus y over omega in the y direction. This is the cylindrical basis vector in terms of the Cartesian basis vector. E phi is minus y over omega in the x Cartesian direction plus, come on marker, plus x over omega in the Cartesian y direction. And then z is just z. I won't even make any distinction between those two. Okay? You're familiar with this. We've had E&M. We've had to do integrals using these ideas a billion times. Okay. Right. Okay. Now this basis is technically orthonormal, and in the sense that orthonormal, in the sense that my components of my metric, which are defined as that should be a J, dotted into K, is delta function. Right? You can convince yourself of that by using those basis vectors and doing this operation. Cool. Now, what do we do about the connection coefficients? So let's start talking about connection coefficients in cylindrical coordinates. The connection coefficients, they quantify the turning of the basis as I move from one location to another. So if I imagine in my spherical polar or my cylindrical coordinate basis, I've got an orthonormal basis at any point, right? I can plot that down. But if I were to keep the cylindrical radius fixed and change the phi coordinate, they rotate, right? They rotate. Cartesian coordinates don't do that, right? Cartesian coordinates would stay fixed. Same with Lorentzian coordinates, right? But in general, a coordinate system can still be orthonormal, but the coordinates can turn relative to each other throughout the 3D space. And so the connection coefficients are what we're going to be able to use to quantify that. And so that we can still do algebra using these, okay? So by definition, these are gradient, the basis vector, along K of the J basis vectors, is equal to the connection coefficient ijk times the basis vector EI, or equivalently, the basis vector, or I'm sorry, the connection coefficient gamma ijk is EI dotted into the gradient along K of EJ. So that's how we define it. So let's do the following. This is anti-symmetric. I can prove that by doing the following operation. Take the gradient along K of EI dot EJ. If this were completely orthonormal, of course, this would be a delta function, but that's not necessarily the case here. So in general, just working out the chain rule of this, right? Anti-symmetry would require this. This has got to be 0 for an orthonormal basis, right? This has got to be 0 for an orthonormal basis. That's basically just saying the gradient of the metric, right? And we always say the gradient of the metric is 0. Okay? So working out chain rule for this guy, we get something like EJ dotted into grad K EI plus EI dotted into grad along K of EJ, all that, J, sorry, is 0. But now this, if you look up here, it's our definition of a connection coefficient, right? Both of those are connection coefficients with their indices flip-flopped. So this implies that connection coefficient ijk is equal to, and that's, which one is this? By my definition up there, right. So that's this one right here, in terms of the ordering of the indices. And the differentiation index is always the last one in the connection coefficient, just by convention, all right? So this is going to be equal to the negative of if I flip-flop the first two indices. Of course, the differentiation index is always going to be last, but if I flop the first two indices, it's anti-symmetric in those two indices, just by a chain rule derivation there. Okay. All right. Now let's think about cylindrical coordinates for a second. Okay. So I'm going to look down from above my picture here now, and I'm going to kind of do what I did a moment ago, but we're going to think about this for a second. So if I've got two locations in radius here, two cylindrical concentric circles, it's a little loppy. That's okay. And I were to say, okay, what's the basis vector here in the omega direction? It would look something like that. It would point out straight radially, right? If I were to go out in radius to some other point and compute what the basis vector was, still would point out directly radially, right? No problem. But key is that it's not only pointing in the same direction, it's the same magnitude, right? But now if I do that with the, that's just bothering me. If I do that, that's worse. If I do that with the phi component, what I want to know is, okay, let's go out here. I'm going to draw this a bit exaggerated to give myself room. And this is the basis vector in that direction. What I want to know then, and then this is the basis vector in the phi direction. What I want to know is, as I move along one of these coordinates, how does the other basis vector change? So if I were to move along the phi coordinate at constant radius and compute what the radial basis vector is, it would actually move, right? I'm exaggerating a little bit here, but you can see that as I move along the circle, right, the direction of this radial basis vector doesn't transport like this, it transports like this along that coordinate. And so there is some turning of the omega basis vector as you move along at constant radius, as you change the phi direction. And it is this sort of change here that we want to get at, which is the grad along phi of the omega basis vector, right? How is it changing as I change phi? That's what we're getting at. That is what the connection coefficient is. And you can do this by inspection, just by looking at a plot or looking it up in the cover of Jackson. We know this, right? We can write this down. So the gradient in phi, along phi of the omega basis vector is just the phi basis vector over omega. And the gradient along phi of the phi basis vector is just the negative that, the omega basis vector over omega. Just by reading off the plot, basically. Okay? So now looking back at my definition of the connection coefficients, I can write down the connection coefficients, right? And they would be, so gamma omega phi phi is equal to minus 1 over omega. And then gamma phi omega phi is equal to 1 over omega. And then all else are 0. In 2D. I've only drawn this in 2D. Okay. These connection coefficients become extremely important for doing differentiation in non-orthonormal bases and completely general bases, and then therefore in curved spacetime, which we'll get to. Okay. So if I were to define some tensor W as the gradient of some vector, I wrote it down in my notes as xc, but that's a lot of squiggles to write. So I'm just going to write some general vector A because it's true for any general vector A. So if you look at my notes online, I used xc. It's the same. Writing this out, we would have the grad along K of AJ EJ, right? That's just definition. I'm not making a distinction between covariant and contravariant here because this is purely Newtonian flat spacetime. But go with me for a second. This is equal to gradient of K. I missed an indice there. AJ EJ plus AJ times the gradient along K of the basis vector EJ, right? Just chain rule, just chain rule. All right. Now, normally, you wouldn't worry about gradients of the basis vector in Cartesian, right? But here we have to worry about them. Okay. And so that's equal to A. I'm going to rewrite this using our comma notation, right? AJ comma K EJ plus AJ connection coefficient L J K E L, where I just use my discretion to change the index. Doesn't change the meaning because I'm summing over it, it gets strangled. Okay? Or in components. So then my tensor W, Wik, is going to be equal to A, I, semicolon K, where now I am defining that as the full gradient, right? You remember before when we were in Cartesian Euclidean space, we didn't really make a distinction between the commas and the semicolon. They're the same thing. But now when you go to completely general bases, there is a difference between a comma derivative and a semicolon derivative. The semicolon is the full gradient. And it is built up off of that comma partial derivative, AJ comma K, plus connection coefficient IJK AJ. Which again, in a Euclidean Cartesian basis, the connection coefficient is 0, and so then there's no distinction between the semicolon derivative and the comma derivative. But here there is. Now, that's how I would write a completely general gradient, which again, a gradient, real gradient, increases the rank of whatever you're doing by 1. And so a gradient of a vector is a tensor, which is what we got there. Now let's extend this to space-time and completely general non-orthonormal bases. And when we go to this, so let's talk differentiation in non-orthonormal. So since my basis there, even in cylindrical coordinates where I've got non-vanishing connection coefficients, that's still orthonormal. But in order to treat curved manifolds, we have to be able to handle non-orthonormal bases. And so here, we have to distinguish between contravariant and covariant components, just like we talked about last time, right? That's the thing that you really have to start wrestling with when you deal with non-orthonormal bases. And so there in my connection coefficients, I didn't worry about it, right? You could have stopped me when I wrote this, because, well, shouldn't I have used the contravariant component there? Really, I should have. But it doesn't matter. For that, it didn't matter. But here, we need to. So the general connection coefficient definition is the following. Gradient along beta of E alpha, where now I am using Greek indices to indicate space-time, is defined as, of course, the gradient along the basis vector beta. That's just a notational definition there when I write the beta underneath the gradient there, of E alpha, which we're going to define as now contravariant mu alpha beta E covariant mu. Okay. Now we can use duality, which tells us that E nu dotted into alpha is equal to the Kronecker delta nu alpha, right? That's how we define our dual bases from last time. So this tells us then from duality that the gradient along beta of E contravariant mu, which of course we've already defined this, this is going to be equal then to minus the connection coefficient mu alpha beta times E alpha. Yeah. Okay. Same deal. So if I wanted to write out this connection coefficient mu alpha beta, it would be E mu dotted into the gradient along beta of E alpha, which was our definition. I've erased it already, but that was our definition. This is going to be equal to minus E alpha grad along beta of E mu, contravariant, the dual basis. That's also a result of duality. So just watch your signs. Okay. So now let's consider a gradient of a vector in non-orthonormal basis. So gradient of a vector in general. A, mu, contravariant components, full gradient beta. And we're going to do this mu. So this is the gradient. This is defined as the gradient along beta of the vector, right? I've just taken contravariant components, matched that up with the basis vector. That was our definition for the geometric object of a vector using the contravariant components. And that's then going to be the same as this. I've already written this, just said it in words, like that. Okay, so let's do some chain rule. In we go. Gradient along beta of a mu, e mu. And of course, I haven't given myself enough room. Oh well, we'll write it down here. You know where I'm going with this. Gradient along beta of e mu. U. All of that then is equal to this first term, that's the partial derivative, comma beta e mu plus definition of our connection coefficient comes in, and we can write this then as a mu connection coefficient alpha mu beta e alpha, where I've taken some liberty to change the indices because they get summed over, and so it doesn't matter. All right. And then finally, all of that then is equal to, I can factor out the basis vector, and again, I can change this at will since it's a strangled index. Comma beta plus a alpha gamma mu alpha beta, all in the marker dying, really dying e mu. Okay, so I just changed the indices, which I'm free to do, and I brought out the basis vector. And so now I have the full gradient in a non-orthonormal basis, which depends on the connection coefficients, u, gamma, mu, alpha, beta. So if those vanish, this returns to what we were used to before. Right? This is, look at this, right? It's like they're right next to each other even. It's the same thing. Right? But now I've extended this to treat non-orthonormal bases in space-time. And so now the up and downness of my indices matters, and I have to be careful about that. Okay, so the comma derivative is the result of letting a basis vector act as a differential operator on the component of the basis, the component of the vector, right? I'm letting, it's a partial derivative. Right? I'm keeping everything else fixed. I'm saying, how does it change along this basis vector? In a way, treating the basis vector like a differential operator. Okay.
I just have a question about the notation in the first line here on the left side. So the semicolon doesn't like indicate that you're supposed to, or I get that you're supposed to differentiate the unit vector as well, but it's not obvious from the expression.
Right. So.
Just general,
the general question about the notation of the semicolon. So do you mean this basis vector here?
Yeah.
Okay.
Because on the next line, you differentiate both.
I do on the next line. Right? So I am actually defining this. So I'm actually, this is subtle and this is a bit trickery. I'm not actually taking like this basis vector and pulling it over here. Maybe this is starting to confuse me too. So going from here to here, this is clear, right? This is clear because here I'm using my contravariant components and I'm re-expressing this as this. And I guess all I mean by this is a notational definition. Anyone want to help me out? Got a better explanation than that?
I think that a mu, e mu, because the indices are the same, that holds that represents the vector itself. Right. It's less. Right. You're not operating on a component and a vector. Yeah. The a mu, e mu, like that is the place.
Thank you. Yes. Thank you.
So we wouldn't include the vector in this notation if the index wasn't strangled.
Right. And so that's actually the last line that I haven't written yet from my notes, which is to eliminate on both sides of this equation the E mu, right? So then I can express, which you should have caught me when I was equating these two things because they're not equal, right? Alex caught me, he didn't say anything because I skipped the last step, which I've written here in my notes, which is A mu semicolon beta, come on baby, is beta plus A alpha gamma mu alpha beta, right? The full gradient. So I stuck that here so I could eliminate it here later.
I think I see what might be confusing them too.
Okay.
So on the first line there on the right-hand side, that would be a rank 2 tensor. So the result of that. On the left-hand side, it's only showing as rank 1 because you're strangling the
Right. Well, but this is actually rank 1 because this isn't the full gradient.
Yeah.
Right. I'm
Well,
taking the
it's
gradient
a
along the
directional
gradient direction. It's a directional derivative, exactly.
Yeah, but you're not explicitly writing it, so I think
That's okay. Yeah, that's the confusion.
Yeah. It should be like E
Yeah.
dot that.
Okay. Yes. Yes. Yes.
So,
Go ahead.
would it work to have the A mu and the E mu in parentheses and then the semicolon data
Outside of it. Outside of it. Yeah. So you could write this. Is that true? No, because that would imply the full gradient. So the semicolon is the full gradient, not the directional derivative. So for instance, you were saying something like this.
But with semicolon and then, yeah.
You were saying this, right? No, that's right. Yeah, notationally that would be the same. Everyone agree? Yeah. Because that is a directional derivative then in the beta. Thank you. Okay. So the way to think about these connection coefficients is that they correct the gradient, right? Or they really correct the partial derivative. They tell you how much the partial derivative differs from the full gradient. And so they're correcting indices of that gradient.
It's the other line on the left of this one, it's the top one in the middle. The way it's notation.
You mean
the
this
middle?
one?
No, the top line middle term.
This one.
Yeah, it's cool.
Yeah.
Yeah.
Yeah, yeah. Exactly. Yeah.
So the beta is actually the E sub beta.
Yeah.
It's kinda- okay.
Yeah.
That makes sense.
Okay, cool.
Yeah, it's just not, it's a notation. Not,
It's a total notation thing. Exactly right. Exactly right. Okay, we could do the same thing for tensors. And end up with, let's see. Okay, one last step. So here I'm taking derivative of the contravariant. The covariant is similar. So if I wanted the covariant components, they would just be A alpha semicolon beta, A alpha comma beta minus the connection coefficient mu alpha beta A mu because of our duality relationships over there. That's the only thing that changes when you're doing the covariant versus contravariant with the connection coefficients. Okay. Tensors. Fairly similar, but now you can think about this connection coefficient as correcting one of the components of the gradient, right? And so now if we've got multiple indices in a higher ranked tensor, we have to correct each index, right? We've got to correct all the indices of that gradient. And so now we're going to write this out. Oh, I did this repeatedly in my notes. F's and gammas, not the same, but my hand wants to write them the same. F alpha beta comma gamma plus gamma alpha mu gamma F mu beta. And have I gotten, I'm almost out of the camera frame. And I'm sorry, remote viewers, Just look at the notes. I can write it down here. All right, where was I? Gamma, beta, mu, gamma, of course, F, alpha, mu. So now I get this extra term because I've got to correct both indices, the alpha and the beta indices. Okay? Just to make sure I wrote all those terms up there correctly. Yeah. Okay, and then for the covariant components, alpha, beta, semicolon, gamma, gonna be similar. F, alpha, beta, comma, gamma, plus, oh, of course, minus gamma, come on, baby, mu, alpha, gamma, acting on F, mu, beta, minus gamma, mu, beta, gamma, F, alpha, mu. It's the same. The indices are in the same order, but I flipped the signs on the connection coefficients to honor duality. So now we're correcting both the alpha and beta indices to get the derivative correct. Okay. So actually computing the components of the connection coefficients and general non-orthonormal bases is hard. With cylindrical coordinates, the way we just did it, we just looked at a picture, right? And we by inspection derived the coefficients, the connection coefficients, components of the connection coefficients. The procedure for doing this in a general basis is complex, and I'm going to write it up because you might need to use it for homework. But the short answer is use software. This is going to be a side project for you all. So I've got some links to some software that you can use for doing this. The most well-known one is a Maple library. Did anybody use Maple? Yeah, I have too. I wrote my first author paper deriving everything in Maple. But it's called GR Tensor from Hartle. And it's just what gets used, right? Because computing these things by hand, which is what I did when I first learned GR, fills boards, just completely fills chalkboards. And then you end up with some simple expression at the end where you chalk. But here's the procedure, right? So one, evaluate the commutators, which is why I showed those commutators, okay? So we're gonna say, put in my basis vector E alpha, comma, E beta, right? We're gonna define something called the commutator coefficient, right? Which is this C alpha beta rho upstairs operating on E rho downstairs. So I need to compute these C's, these commutator coefficients for some basis, okay? So in other words, C alpha beta rho upstairs is defined as E rho upstairs dotted into the commutator operator, right? Which we had before. That expression involving differences of the vectors. Okay, so once you've got these, step 2, you need to lower the first index. Last index. That was silly. It's written as last. I read 1 ST in my notes, right? I was like, the first index is already lowered. Lower the last index, right? Bring that down. How do we raise and lower indices? Metric, right? So C alpha beta gamma now is going to be equal to C alpha beta rho. Use the metric rho gamma to lower that rho, strangle it, make it a gamma on the bottom. Cool. Step 3. Now we compute the following. the fully covariant connection coefficient, gamma, alpha, beta, gamma, which is going to be defined as 1/2. God, this all brings back memories, nightmares for me. I remember doing this. And I'd forgotten about it until I started writing up these notes, and I was like, oh my God, I have graphic memories of doing this on the board. Didn't know that about myself. So these are gradients, well, partial derivatives of the metric, minus g beta gamma comma alpha. I'm going to write this on the second line now, plus our connection coefficients, or our commutator coefficients. Alpha, beta, gamma, plus C, alpha, gamma, beta, minus C, beta, gamma, alpha. Close bracket. All right, so note, these are partial derivatives of the metric, and the ordering of the indices on the G's is the same as the ordering of the indices on the C's, but the C's, that's not a differential operator. Those are just the components of our commutator coefficients. All right. So what happens to this then if I assume a coordinate basis? Let's assume that E alpha and E beta are a coordinate basis. How's this change? You tell me. C's go to 0. Great. Okay. What then if I decide that maybe it's not a coordinate basis, but it's an orthonormal basis? Metric derivatives go to 0. So in an orthonormal basis, the derivatives of the metric are 0. Right? And so that goes away. That actually implies, if you then plug zeros in here, that in an orthonormal basis, these connection coefficients are antisymmetric. You get some minus signs in there from the commutator coefficients. Okay, so the last step to get my actual connection coefficients that I need for computing these gradients is to raise the first index of that guy. Okay, so finally, raise first index. Same deal. Gamma mu alpha beta is going to be equal to G mu alpha gamma alpha beta gamma. In a coordinate basis, not necessarily orthonormal, but a coordinate basis where the commutator coefficients vanish, these are called the Christoffel symbols. If you see that word floating around somewhere in whatever we read. Specifically, this in a coordinate basis are Christoffel symbols. They characterize the curvature, really, right? They become fundamental to describing the curvature of curved manifolds when we actually start to do dynamics, interesting things, right? And that comes out here by changing the way that we do differentiation. Okay, so computing these is a pain. Use software. Side project. I'd like you all to. I think I put the link to the Hartle stuff in the syllabus or somewhere on the webpage. I can't remember. If I didn't, I'll post it. Go take a look at that. There is also some stuff I found digging around in Python. I'd be very curious to see if you all can come up with, find something that's useful, that's better, maybe, that you find handy dandy for computing these things. Obviously, there's the Maple stuff, but we might not have access to Maple, all of us. There's a site license for Mathematica. I know there's a Mathematica package that does all of this. So just for my own purposes, I'd be grateful if you all explored that and found what you thought was the most useful for computing these things. it will be useful to you too, because it's going to make your life a lot easier in doing the homework problem. I know for the class, you know, the ones in Hartle, like that Hartle has made available are good, but they've been around forever. Like they're pretty old, right? Like who uses Maple anymore? So I know there must be something better out there. Okay. Questions? I'm gonna move on and briefly talk about integration on curved manifolds. Okay. Integration. Generally. So in 3D Euclidean space and Minkowski space, where we have Lorentz bases, what tensor was critical to computing integrals? The Levi-Civita tensor, because it gives the sense of volume in some space, right? And so if we're going to do integrals over space, we need that Levi-Civita tensor, okay? But what we need is the Levi-Civita in a completely general basis. That's what we need. It will turn out then, and the book spares the derivation, you can go look at Misner, Thorne, and Wheeler if you really care. It turns out that in a general basis, the components of the Levi-Civita tensor net factors that go like the square root of the determinant of the metric. Okay, so that gets folded in there. That's actually, at the end of the day, a pretty simple modification. And so we're going to need square root of what I would just call G, which G is defined as the determinant of the matrix representation of the metric. By definition, okay? So let's say that components of the orthonormal, I'm just going to write that as ortho, Levi-Civita tensor. Let's write those out using the square bracket notation that the book uses. Okay, bracket, alpha, beta, da, 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 all the way up to nu, whatever the dimensionality of your space is. Okay, recall that this is +1 if alpha, beta, and gamma are even, right? It is equal to -1 if it's an odd permutation of 0, 1, 2, 3. I think it's had it. I think it's had it. We're going blue. We're going blue. And it's 0 if they're not all different. We remember that. In a general non-orthonormal basis, we use that square root of the determinant of the metric to correct those coefficients to account for the curvature. So, in general, alpha, beta, da 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 da, nu is going to be equal to, so the covariant components of Levi-Civita come in like this. Absolute value of the square root of the determinant of the metric. Word salad. Alpha, beta, dot, 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 nu. Where that's my orthonormal component of the Levi-Civita tensor. And then for the contravariant components, alpha, beta, dot, 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 nu, this is going to be 1 over the square root of the absolute value of the determinant of the metric, alpha, beta, dot, 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 nu. Okay? Oops. Plus minus for the contravariant components, where the plus is for Euclidean space and minus is for space-time. Let me write that out. Plus Euclidean minus space-time in Minkowski. Okay. Let's do an example using the general Levi-Civita in spherical coordinates, where we have some turning of the basis vectors, right, in spherical coordinates, right? So we have non-vanishing connection coefficients, and so we should have some interesting integrals, right? So let's think about this. We're going to restrict ourselves to Euclidean space for simplicity, Euclidean spherical coordinates, where I'm going to represent that by the spherical radius theta phi in the usual ways. Okay. Here, I can't remember if we did this last time. I certainly wrote it down in my notes, but I can't remember if I wrote it on the board. The metric components are G, R, the pirate's favorite component. 1. My son thinks that's a funny joke. G theta theta, R squared, and G phi phi is R squared sine squared theta, right? I think I might have skipped this in lecture, but you can do it by the same way that we got the metric components and cylindrical coordinates. Basically look at how the basis vectors are changing, and then compute their dot products. Okay, so therefore, if I were to take the determinant of that thing, treat it like a matrix, right? It's a diagonal matrix, all the other terms are 0. Take that determinant, that's pretty simple, which is the determinant of this thing treated like a matrix. I shouldn't write alpha beta there. I did in my notes, but this is 3D, I should write IJK, right? I should. This is pretty simple. R to the 4th sine squared theta. Wham. Okay. So now, how do we get the volume element in some space?
Or the basis vectors.
The base, you insert the basis vectors into Levi-Civita tensor, you get some volume element. Okay. So in general, the volume element is, we use it. Ooh, that's ugly. That's uglier. D sigma. I'm going to get that from Levi-Civita tensor by inserting into it these basis vectors. Some infinitesimal dr in the r direction. Remember, partial r is just the basis vector in the r direction. When we were talking about tangent spaces and curved manifolds, we redefined the basis vectors as the partial derivatives along these directions. Okay? And this is some infinitesimal change because I'm looking for some infinitesimal volume element. And so now I've inserted those basis vectors, right? I shouldn't call them unit vectors because I haven't specified that they're necessarily orthonormal. In fact, we know that these can change in their magnitudes depending on where you go, right? Because of the turning and the changing of the basis vectors with respect to each other. Okay, now this is a tensor, and so it is a linear function of vectors. Using the linearity relationship, I can rewrite this as the r theta phi component of Levi-Civita times dr d theta d phi, right? Because just I can pull out and I can make a sum, and then I can stick the basis vectors in by themselves. And when I stick the basis vectors in by themselves, I just get components, which is what I did there. Okay? And so I've got the component of the Levi-Civita multiplied by all the other components go away. Okay? Now, in a general basis, this is square root of G. These are covariant components, right? These are the covariant components. Dr d theta, d phi. And what does this end up looking like? R squared sine theta, dr, d theta, d phi is the volume element in spherical coordinates. Ta-da! Right? You knew that. But this is a completely general way of doing it, right? This is the simple example that is very familiar and makes you feel warm and fuzzy. Things get weird in completely general, non-orthonormal bases, right? But the procedure is the same. This is how you would compute the volume element in some arbitrary coordinates, arbitrary space. Okay. Then, on curved manifolds, we'll deal more with what I'm about to say later when we actually try to derive the conservation laws in GR. But curved manifolds, integration is hard. And in one particular way. So take, for example, the integral around some surface bounding some volume V. So a surface integral of T alpha beta d sigma beta. Now remember, this is now the unit vector of that surface, right? By sticking a component on it, I'm talking about the unit vector normal of that surface. And so this thing is a vector, right? This is our dot product, right? We did this, right? When we were deriving momentum conservation, we did exactly this integral. We used Gauss' law. We made everything happy and got a divergence. In curved manifolds, this is actually a very tricky integral to do. Why is that? It's this idea of different tangent spaces. And so vectors live in tangent spaces. And when we computed the gradient operator, where we said, okay, I want to compute the gradient of a vector, right? So I need to transport this vector, which lives in a different tangent space over here. I need to transport it to the same tangent space where I want to compute the gradient, and then compute the gradient there in that tangent space. That's the way that we did that with the gradient operator, right? And so we came up with a transport law for how to do that correctly to create differential operators on curved manifolds. This gets hard because everywhere this vector on this surface, right, that's bounding this volume, that vector normal to that surface lives in a different tangent space. And so now you've got to transport all of those possible infinitesimal vectors, an infinite number of them really, you've got to transport them to the same tangent space in order to compute the value of this integral correctly. Now it turns out you can't really do that, because the transport law for the vectors in this case is sort of ill-defined. You can take multiple paths, and there is no preferred path to do that transport, right? So I have some freedom to choose how to transport all those infinitesimal vectors to a common tangent space. Put another way, I could pick any of those tangent spaces in which to do the integral. And so the value of it actually depends upon the path taken, and there is no preferred path for transporting those infinitesimal unit vectors. And so this integral is not fun. In fact, question? Yeah, Eric.
So you're about to write it. It's ill-defined then?
Yeah.
Correct. Or the volume integration?
So what is ill-defined? Yes, let me spell this out very clearly. So this particular integral is ill-defined because it involves the integration of a vector. Okay, so the integration of a vector on a curved manifold in this way is ill-defined. What is not ill-defined is this. So I'm going to do the same surface bounding the same volume in 4 space. It's an ugly sigma. sigma, what did I write in my notes? Alpha, of course. Okay. That's fine. That's a scalar. That's a scalar. I don't have to worry about tangent spaces. Scalars are scalars. They just exist on the manifold. And so integrating them around the surface of some volume in even in a curved manifold is well proposed. That is a well-defined problem. So if the result of the integration is a scalar, you're good. The result is a vector, it's ill-defined, and you can get multiple answers. This will rear its head when we try to formulate conservation laws, because that's the way we did it, right? We wrote down these flux tensors for whatever thing that we wanted to be conserved, and then integrate around the surface, use Gauss's law, and do the whole thing. This will rear its head again when we try to write those down in general relativity. Okay. Cool. All right. How much do I put? Oh, more than I thought. All right, I'm going to skip that. This will come up when we deal with the stress energy tensor and momentum conservation. And so one of the problems you have is to derive stress energy tensor, so I'm going to skip this part. And we derived the stress energy tensor for a perfect fluid in the last chapter, so you're familiar with that. So I'm going to skip ahead a little bit in my notes. So there's some extra stuff here, which is basically just talking more about how these integrals for conservation laws are tricky. It's not much. But let's talk about proper rest frames. And if we could get through this, that would be good for today and for this chapter. Okay, so a proper rest frame. Consider an accelerated observer with a 4 velocity u. Okay. They're accelerated along their 4 velocity. So computing that acceleration is just the directional derivative along the velocity of the derivative. What's their acceleration? 4 acceleration. Okay, so now I'm going to construct what we're going to call a proper reference frame. And it's going to have the following features. Okay. 1, the spatial origin will always be at the world line. Spatial origin on world line of the observer, which is a way of saying that the coordinates j hat equal to 0. Okay, so when we're dealing with the proper reference frames, I'm going to use hats on indices, just like the book does, to denote proper coordinates. Okay. I'm getting tired. I shouldn't call this necessarily a rest frame because the particle doesn't have to be at rest. I should call it the proper reference frame. Okay. The other property is that along the world line, the time coordinate, x 0 hat, is a proper time tau, as measured by the clock that the observer carries with them. Okay. Third property, near the world line of this particle, these coordinates, the 3 coordinates, the spatial component, right, xj hat, measure physical distance on a Cartesian lattice. So this is our little local sort of Lorentzian reference frame, right? So locally Cartesian. I've got some Cartesian lattice that around the location of my world line at constant proper time at least looks Cartesian. And I can measure things in a 3D Cartesian kind of way. Okay? This implies that in that locality around the world line, the metric is alpha hat, beta hat of eta dx alpha hat dx beta hat, which is another way of saying that G, the components of the metric alpha beta, which are equal to dx alpha partial dotted into partial of x beta, is equal to the flat metric alpha beta at x j hat equals 0. Okay. So at the world line, at the origin, it looks like flat space. Cool. Now taken together, item 1 plus item 2 imply that the time unit vector in the proper reference frame, which we define just as that, right, just by definition of the unit vectors, is equal to u, the 4 velocity. Right? Okay. In general, this reference frame can be rotated. And so you can have some, you can say that it can rotate with a vector angular velocity omega. And the components of that are as follows. We're going to say that the time component is 0. All right, so this vector omega, which characterizes the rotation of my inertial reference frame, is going to be completely spatial, right? There's going to be no component outside of the slice of simultaneity of the 3 space at some constant proper time. And therefore, the j's are not equal to 0. I don't know what they are, but we're going to allow this reference frame to rotate. But we're not going to let it rotate in space, or in time, only in space. Because we're not crazy. That would be so hard. Okay. So then, I'm not sure I'm going to get through all of this. The acceleration of that observer of the frame, acceleration of the frame of this proper reference frame, which is also the same as the acceleration on the observer, right? Because we're using the observer to define what this proper reference frame means, even. And so this acceleration is both the acceleration of the frame and of the observer. Is a0 hat is equal to 0, and then a j hat is equal to, well, just the j component of the acceleration, measured acceleration. So in other words, it's all spatial also, right? We're only going to allow this acceleration to occur in the spatial directions. Now let's talk about its connection to the other important idea of reference frame that we have developed, to inertial reference frames. It's not the same. The proper reference frame is not the same as an inertial reference frame. Okay, but you can connect the two. Okay. So let's say that we want to transform between the proper reference frame and an inertial reference frame at some event in space-time. And we're going to choose an event that is x 0 hat equals 0, and conveniently j hat equals 0. So we're going to put the time origin and the spatial origin at this event, and around that event we're going to transform from inertial to proper reference frame. Okay, and so there, because of all these other properties of proper reference frames, the transformation of the coordinates, these are now the coordinates in the inertial reference frame, spatial coordinates in the inertial reference frame, is going to be equal to the spatial coordinates of the proper reference frame plus 1/2 the acceleration in these various components evaluated at the time x 0 hat plus Levi-Civita I hat j hat k hat, the angular momentum vector j coordinate, that's a hat, coordinate time 0.
Let's do time square with the acceleration.
Thank you. Which is just straight from kinematics, right? Just straight from kinematics. Same with this. So this is just the vectorial displacement due to some acceleration, right? And then this is just a Coriolis force. Because remember, Levi-Civita in this way generates a cross product, right? And so this is just taking a cross product. And then multiplying by time, right? Because I get a Coriolis acceleration and multiply by time to figure out the vector displacement. Okay. The other thing that we need, so these are the spatial components. The time component is Lorentz boosted between these two inertial frames and the proper reference frame. So a Lorentz boost will give us, for the time component in the inertial reference frame, is equal to the time component in the proper reference frame all times 1 plus acceleration, oops, that's a G, acceleration J, that's the covariant component, times the contravariant component of coordinates. Just a Lorentz boost is all that is. All right, how much more do I have? I can do this. One last thing, and then we're done. So then, metric in an inertial frame, this we've had before. That is always just going to be ds equals minus dt, well, I'm going to write it this way, squared, plus delta function ij, and then the spatial components of the displacement, like that. So there's our inertial reference frame metric line element, same difference. Okay, so using these transformations over there, I can get the metric in my proper reference frame by transforming this inertial reference frame metric into the proper reference frame using those transformation laws. Okay, and so then the metric in proper will be ds squared is equal to minus 1 plus 2 acceleration dotted into position vector all in the time component squared plus 2 times angular velocity vector cross the position vector, that's a Coriolis term, times the position vector and then the time component in the proper frame, plus delta ij dx j hat dx k hat. Okay, where these are 3D space vectors. just as a caveat. So when I write these out, right, these are just the 3D space vectors, because remember, these were only this acceleration we said didn't have a time component anyways. So I don't have a good way of distinguishing between 3 vectors and 4 vectors. I just use the arrows. But each of these vectors that I've written here is a 3 vector, right? I said the omega didn't have a time component. So it almost doesn't matter. So that's the metric, right? This again is like a Coriolis force. If the frame's not rotating, that term goes away, but you still have this Lorentz boost-like factor on the time component between the proper and inertial frames. Yeah.
So with the twins paradox, is that term what, so when they turn around, is that the term that like changes the time?
It's the acceleration. Yep. I mean, that's the classic resolution of the twins paradox, right? Who's accelerating? Yeah. Okay, so the last thing that I didn't get to, and I probably will not until we need it again, is the geodesic for a free-falling particle. I think, do you have something like that in the homework? I know that you're going to derive this proper reference frame stuff, so I wanted to do the very basics of it up on the board. So one of the problems is a proper reference frame problem, so we want to do that.
This is the last problem, I think the last part of it is.
I remember what it was. So read over the geodesic for a free-falling particle, because one of the problems requires you to compute the connection coefficients, which are then required to fully express the equation of motion for a free-falling particle for its geodesic. So just, that's where that problem would go. But other than that, that's it for chapter 24. Questions? For next week, read chapter 25 and start working on those problems, and I'll also come up with some solutions for them, maybe. All right, cool, thanks. Bye, Alex.
Take care.